Okay, so welcome all to this third seminar of the year of this series of DaSCI seminars. Today we have with us the Professor Salvatore Cuomo, who is an associate professor of numerical analysis at the Department of Mathematics and Applications, Ercacipoli, at the University of Naples Federico II of Italy. He received his PhD in 2004 in applied mathematics and computer science from the same university. He's been a visiting researcher at the Case Western Reserve University in Ohio, USA, in 2016. And he's been also visiting professor at the University of Geoscience of Beijing in China in 2019. He was the founder of the company Proyecto, which is an innovative academic spin-off that deals with AI solutions and data analysis. And his research interests are in applied mathematics topics, more in detail in numerical approximation problems, multivariate data analysis, and scientific machine learning. He's been involved in several research and development projects in the research areas of scientific computing, data science, and Internet of Things. And he's the author of more than 150 research papers in international conferences and international journals indexed in Scopus and WOS database. So, Professor, thank you so much for joining us, and the floor is yours.
Okay, thank you for your kind invitations and presentation. Okay, I will speak about a computational paradigm in scientific machine learning, and this is a brief overview of my talk. I will speak about what is scientific machine learning, a topic that is related to scientific machine learning, that is the physics-informed neural network, some theory about physics-informed neural network by learning point of view, some application to forward and inverse problems, and just an idea to how to overcome some scientific machine learning limitation, and finally conclusions. About AI and mathematics, it is clear that now AI is something that is pervasive in our society, as for example, for autonomous driving or speech recognition, but also by science point of view, as for example, in molecular dynamics. So it is very interesting for us in mathematics how to rigorously explain some foundation of AI, and this is mainly something that is mainly empirically driven. About two important books on these topics, I will call your attention on the first one, that is Deep Learning Architecture and Mathematical Approach, and the second one is very interesting, 2023, by Philip Gross and Gitta Kutiniok, that is Mathematical Aspect of Deep Learning. This is why because scientific machine learning is something that is related to data, mathematical models, and surely something that is high performance computing, that is the infrastructure of scientific machine learning. In these novel paradigms, data and mathematical models are used to enhance predictions in some applicative context. About this, in scientific machine learning, we can recognize several main fields of interest. The first one is about the foundation and mathematical foundation of scientific machine learning. The second one is focused on tools, as you are a computer scientist, so you use surely PyTorch or TensorFlow as tools for scientific machine learning, something that is related to the applications, and a lot of idea about models, especially in deep learnings and Bayesian methods and other kind of modeling. The interest of scientific machine learning is referred to a potential market of this research field. It is planned that about $23.7 billion will be invested in simulation solution and product with respect of scientific machine learning. Surely, high-performance computing is something that is an infrastructure in this market, but two killing applications of scientific machine learning are related to bioscience and engineer applications, especially, for example, in semiconductor or materials design. This is, in my opinion, very interesting because by mathematical point of view, when we want to make a novel AI model, we have to take attention to two key concepts. The first one is how to design a model, and the second one is how to assess this model. About the design, one thing is related to the expressivity. The expressivity is something that tell us how efficient and accurate is solved a problem, and this is, for mathematical point of view, something that is related to approximation theory. About the word learning, this is referred to some algorithms that are quite good to minimize a function of a lot of parameters, and it belongs to optimization theory by mathematical point of view. By assessment key concept, we can recall something that is related to generalization of a problem. That is the reason why a model is so good. And this, by mathematical point of view, is linked strictly to stability and convergence of a model. And finally, computer scientists take a lot of attention in XI now, explainability. And for a mathematician, explainability is something that is related to well-posedness of a problem and existence of a solution or fixed problem. This is, in my opinion, how it is possible to link AI models to mathematical foundation in terms of design and assessment. Sure, for mathematicians, a neuron is something that is related to a capital M that is a subset of Rn, W that is a matrix of weights, B that is a real number named scalar, and other parameters that are named hyperparameter. And two important functions. The first one is the aggregation function. The second one is the activation function. In other words, if you want activate a neuron, we have to think to a map that from capital M to R give us, starting from an input eta, a parametric function that depends by W, B, and theta. And it is a composition of aggregation function and activation one. By mathematical point of view, a neural network is a composition of several activation functions. In other words, the information passes from a layer L -1 to a layer R by using a nonlinear mapping from an affine transformation of the previous input eta L and -1 plus theta L, and applying the activation function. In other words, we are thinking to a function that is a map from Rn to Rm, that is the so-called neural network. By mathematical point of view, identify a neural network is generally a fitting model. In other words, if you think at a space of parameter function from Rn to Rm, something that is named the space of hyperparameters, we can try to identify the neural function by minimizing something that is the sum of two pieces. The first piece, the First part is something that is a suitable accuracy between a model evaluated in the inputs and some labels. And the second one is something that is related to how to balance the information on the problem that is named the regularization function. It depends of an lambda hyperparameters. In other terms, you can find a fitting models by minimizing the so-called loss function. A lot of choices about capital D and R are related to mean square error of the models and the two norm square of the weights. About scientific machine learning, generally scientific machine learning are used for solving partial differential problems or partial differential equations. In other words, if you have a omega subset over D and we have some data F and G of our problem, we are interested to solve the equation 2, in which capital F is nonlinear differential operator, capital B is so-called initial or boundary condition, and gamma is strictly related to the physics of the problem. Zeta is something that depends from space and time in physics. About the physics-informed neural network, they are discovered to overcome some issue about PD solver. The first one is about something that has an incomplete physics, but a lot of data. If you think at a very complex phenomena in which the physics is not so well known, but you have sensor that can give you some data. In this case, physics-informed neural network are very good, or in other words, or in other cases, other high computational cost problems, for example, inverse problems, and in this case, use deep learning approach could be a solution of your problem. In other words, physics-informed neural network are some things that are used to predict the solution of a partial differential equation by using data and physics in order to drive the model to a correct solution of your problem. And you can use physics-informed neural network in a direct way or inverse settings, in the sense that you can use physics-informed for solving a PDE or for estimating parameters of, for example, a control problem. Now, if you want to collocate pins in a plane, you can think a pin as a kind of methodology to solve a problem by using Galerkin methods, or something that is used to approximate a nonlinear operator as HippONet. In other words, pins are so-called mesh-free methods for solving partial differential equations. They was discovered in 1994, but only in 2017, Raisi and other co-authors rediscovered the physics-informed neural network, because in 1994, there was a technological bottleneck that is related to the computation of the derivative of a nonlinear function of a lot of parameters. In other words, if you want to minimize the loss function, you have to compute derivative. But in 1994, there isn't tools for computing in efficient and accurate way derivative in high dimension. And now we have so-called automatic differentiation that help us to solve this problem. If you have a look in 2024, a lot of papers, thousands of papers are on PIN. If you have a look on Scopus only for the words PIN or physics-informed neural network, you have more than 1,000 papers, but there are a lot of synonyms of this methodology, as for example, physics-informed learning or physics-informed machine learning, and so on. If you look at physics-informed neural networks as a computational tool, you can take into account that from mathematical point of view, you have a mesh-free method for solving a PDE. You have some things that give you a solution of problems, and in several times a unique solution of your problem. But if you think at machine learning perspective, you can think at physics-informed neural network as a novel way to compute things in a machine learning frameworks that can be work in supervised manner if you have data coming from example from sensor, or in unsupervised way if you know only the physics of your problem. So this is a very novel machine learning tool to predict solution of a differential problem. How is made the pin? The pin is made of three main bricks. The first one is a neural network. The second one is something related to the physics of the problem. Here, there is the physics and the data. And some things that is related to feedback mechanism that help you to increase the accuracy of the predicted solution by a neural network. In other words, if you have an unknown U zeta of a problem, you won't recover it with U theta zeta, that is an approximation related to how the neural network can compute an approximation of your PD problem. Everything is strictly related to the learning process. The learning process is given by the sum of three pieces. The first one is related to the physics of the problem. The second one is related to the boundary problem, and the third one to the data. And if you combine these three pieces by using some hyperparameters that are the weights about physics or weights about data, you can give a learning mechanism to predict the solution of your problem. In a lot of problem, you can choose the loss function for the physics as the residual of the PD equations, and for the data, the residual with known data on the problem. Now, coming back to the mathematics foundation of this kind of methodology, you have to link the approximation of deep learning models directly to complexity of the models in terms of memory occupancy. You can define a so-called matrix of the complexity of your networks that is related to the weights of the networks and to the biases in norm zero. In other words, you can think at a subset of L2 that is a functional class set. In the next slide, we will name Hn as expressivity set, in which if you can estimate gamma star Hn, a measure of the accuracy of on Hn of your neural network. In other words, you can try to have a results of how good is your the solution of your problem. In other words, you can think at a network that by ideal point of view has few non-zero weights and can good approximate the solution of your problem. Coming back to the theory, this is a very interesting theorem, because the first theorem after Shibenko theorem, that Shibenko theorem tells us that with a neural network with one layer and a lot of neurons, we can approximate any linear continuous function. In this theorem, due to Gitta-Kutiniok and other co-authors in 2019, here we have that if D belongs to capital N and sigma is a suitable activation function, if this is the learning function of your problem, you can approximate your learning function with a neural network very well. and the approximation is independent by the algorithm. This is a very surprising result because it tells us that it is possible to approximate the learning function by independent by the optimization error of our problem. And this is a very strong theoretical result about approximation theory. Another result is related to how many training points it is necessary to have in order to well approximate a neural network. This is another interesting theoretical result that is that tells us that it is possible to approximate any neural network with a 3 layers neural network with capital N training points that satisfy this inequality. In other words, deep neural networks are very good approximators. Now, coming back to my research topic, that is numerical analysis. If you have solved in your life a numerical analysis problem, you won't recover the solution of your problem by computing something that is an approximation. But the main theoretical idea is to estimate the global error between the predicted solution of your problem and the exact one. In other words, we want to find a set of parameters that give you an error that is equal to 0. In the PRIM framework, you can think at the predicted solution of a neural network as something that has to converge to the solution of your problem. In other words, you have to select a neural network with some parameters that is quite good to recover the solution of your problem. And this is the hypothesis class set, that is the set of all provided by a neural network solution of a problem with the number of hyperparameters exactly equal to n. And it tells us how is expressive this space in order to capture the solution of a problem. Sure, in this framework, you have to deal with some things that is related to the error. These things is about the L2 norm of the error, the integral between the solution of your problem, real one, and the predicted one. Sure, if you are using some collocation point, you cannot refer to risk of the predictor, but to empirical risk of the predictor, that is the risk of recover the solution of your problem using u hat theta, evaluated in zeta I. It represents how well a neural network can recover your solution by computing u hat star and by using a neural network or training a deep neural network. In this case, your main goal is to have some result about error analysis, in other words, the global error. This is very interesting for our point of view, because when you train a neural network, in particular a physics-informed neural network, you have 3 main errors. The first one is strictly related to optimization error, that is related to the algorithm to compute the minima of the loss function. The second one is the generalization error, and measures how well the loss integral is approximated, recovered by a fixed solution of a trained neural network. And finally, the approximation error is related to how your network is able to approximate a function. In the book of Kitta-Kutiniok, at the beginning of this slide, you can view that the global error is the sum of the optimization, the generalization, and the approximation one. And very few results are known about the estimate of global error. One is about only approximation error by Derrick and Mishra 2021, In this theorem, we have that if you have a neural network with a hyperbolic tangent activation function with only 2 layers, you can estimate in a Sobol space the approximation error by using an estimate that is related to the training points. Another interesting result of the same authors on generalization error is about the Navier-Stokes equation, and tell us that it is possible to estimate generalization error by using an estimate that is related to the dimension of the problem. Unfortunately, this problem suffer of a curse of dimensionality in the sense that when the problem becomes high in dimension, there is a dependence on the estimate on the dimension of the problem. But the same authors in 2022 have a very interesting results about Black-Scholes equation and tell us that for this kind of estimate, there is a bound that depends only by the training point and not by the dimension of the problem. Another finally interesting thing is about inverse problem. If you have a parametric map of a problem, the solution of a problem depends by Y, where capital Y is a subset of RP. In the calibration problem, you won't recover an optimal value that satisfies this equation. Sure, you have to try to any Y in capital Y, and this problem suffer of curse of dimensionality. About the curse of dimensionality, there is a result of Kutinok and other research that tell us that it's possible to find optimal parameter for the calibration problem by using a complexity of the neural network that is polynomially controlled. In other words, these results tell us that trained physics-informed neural networks are a flexible and universal approach to calibrate problems, in particular inverse problem. About physics-informed neural network, the bottlenecks of this methodology is about the training. The training is very difficult because if you want to compute the derivative of highly nonlinear function, you have to extend the network of computational graph. You have to find optimal balancing of physics and boundary and data, and it is done by discover optimal parameters W. And finally, if you think that at each learning step, you have to compute the derivative of a highly nonlinear function, this is very computationally expensive, and most time is spent to computing gradient in optimization or in the learning process. Some key theoretical questions are just still open, that are how it is possible to control a total error or generalization error by using such parameters in hyperparameter space. If it is possible to control the global error by using the generalization error, in other words, if a small pin residual gives us a small total error. And finally, if it is it is possible to bound generalization error with something that only depend by the training points. This is very three interesting question that has to be solved when you want to use physics-informed neural network in an explainability framework. Finally, if you want to use a physics-informed neural network for solving mathematical problems, you have to take into mind that they don't work well when you have to solve high nonlinear problems. If you have some finite elements method that works well, you can try to continue to use this model, and pins are universal approximators, and that doesn't work well with problems with the discontinuities and other things. But if you want to use physics-informed neural network for weak nonlinear settings, these methodologies are quite good. If you want to use it for inverse problem, it's very interesting, and also for high-dimensional problems. Now, I want to show you three main applications of physics-informed neural network. One is a ground flow problem about expressivity and inverse problem. Another is about Black-Scholes observations for a high-dimensional problem. And finally, I want to show you an industrial application that is related to ensemble Kalman's filter. Okay, for ground flow water equation, you have an open subset or Rn. You have something that is a location variables that is related to the diffusing materials, and something that is related to the time. Your aim is to solve this partial differential equation that is a diffusion equation. In particular, you want to recover H, that is the unknown hydraulic head, by have some information about capital SS, that is a specific storage, capital K, that represents hydraulic conductivity, capital VA, that is the instantaneous source thing, and finally delta is the delta Dirac of the problem. The results about this problem are published in a recent paper on computer and applied mathematics with the application in 2023. About this problem, the first thing is how to compute the delta Dirac function. That is a high difficult computation task, and how to approximate this delta Dirac is given in another paper on 2021. So we substituted the right hand of the equation by using a regularized version of a delta Dirac function in a such regularization. The regularization technique are to approximate the delta Dirac function with two main functions in this context. The first one is a cosine transform, and the second one is a piecewise cubic function. And also in this paper, we won't measure the impact of regularization terms on overall solving the problem. How made the pin? The main pin is made by two neurons, one for time, another for the location of the hydraulic head, the ground flow. This is the neural network that is a feed-forward neural network to recover the hydraulic head H. And we use automatic differentiation for the computation of the residual and boundary condition of the problem. This is about the learning process. Here we have the loss for initial condition, the loss for boundary condition, and the loss for the physics of our problem. And this is the residual of the equation. The numerical experiment won't predict the current of dispersion of the hydraulic head in several settings, a single pumping well, but also in a multiple well. It is described in the paper. But here we want to report only some experiments that are linked to the theory of physics-informed neural network. In other words, we select only two experiments for 1 decade and 2 decades. And for this kind of example, we have a closed solution of the problem. We have just solution of the problem, and we use the closed solution of the problem as a benchmark of our problem. This is a setting for physics-informed neural network for 1D and 2D about collocation points in time and space. This is a collocation points for time step, because this is a diffusion equation in time and in space. And finally, this is about how to compute the solution of our physics-informed neural network by using 10 trial of training with 10, 20, and 40 neurons each. In this slide, we report our work at 4 hidden layers with 20 neurons. And here there is only the impact of 2 regularization techniques, the cosine one and the cubic. And you can observe that in terms of loss function, the cosine regularization is a better choice to regularize the problem. But the much more interesting things is about the theory of our field. Our model is able enough to generalize the problem. The question is, by theoretical point of view, if you have a loss that goes to 0, it is not ensured that the solution of a problem is good. And this is due to the case when we enlarge the number of neurons inside the problem, we can observe a mean square error that go up and go down, and we stay in interpolatory part of the model. And in 2 cases, we can observe this kind of a behavior, and we stay in the other end of the pictures. In other words, for 2D in case, we can say that our model deep learning part is not so complex to capture the dynamic of the problem. So our suggestion was, please take attention in design deep neural network inside of the PIN, because it is not so able to generalize the problem. We require in this kind of problem a much more complex network to capture the nonlinear behaviors of the physical problem. About the inverse settings, this is also very interesting because we modify the physics-informed neural network by adding a neuron for predicting capital KX. And this is due by training the model by several values of K and ask to the model to predict something that is not known. For example, capital Kx equal to 5 and 9. And this is a proof us that the physics-informed neural network is a good tool for inverse problem. This is a picture that confirms us that in the inverse setting, the physics-informed neural network works well. About Black and Scholes, our ask is it possible to predict the price of American option by only using a mathematical formulation? This is the Black and Scholes equation that is initial and boundary condition. And the problem is a coupled problem. In one, we have neural network that is used to compute the solution of the problem to price the American option. And the second one is a free boundary problems that is used to simulate the free boundary condition of American options. The problem is solved in 2D models and 4D models. And the very interesting idea is to have a trick to learning this process by using free boundary solution to improve the solution of overall American pricing. As you can view in this slide, the loss function is much more complicated, and this is given by 3 pieces that is related to the first networks and other 3 that is related to the free boundary problems. And also the selection of collocation points is another issue about this problem. And we specify a subtle kind of points for collocation of physics-informed neural network. This is the setting for our experiment, 8 hidden layers, 30 million collocation points for 2D and 100,000 for 4D. This is about training epochs, and this is the algorithmic trick. Each 5 solution of the problem, we use free boundary result of a deep neural network for improve the overall solution of the problem. This is the results in terms of a couple of neurons for the first and second network, we can observe that in 2D models, we have a sort of overfitting when the number of neurons go up, and this is not true in the 4D case. And also by considering the training time, you can observe that if the model enlarges the dimension, the time for training the model is much more expensive in the 4D case with respect of 2D case one. About the industrial application, this is very interesting because we have a collaboration with the Napolitan startup in a railway framework. They have a system that is named Octopus with 8 accelerometers, 1 gyroscope and 1 GPS. And this system is used to predict the vertical displacement of the train. That is very interesting in case of risk of the train monitoring, and also to monitor the safety of the train. This is our physics-informed neural network that in this time is trained by gyroscope and GPS data, and is used in a trained way to give some generative measure to extend the Kalman filter, and in order to improve the solution of the filter in detecting the vertical displacement. These are the result of pin prediction of vertical displacement, and this is about a route from Pianura Pisani, that is a train that goes into place of Naples city, and the solution is very good. Now, in order to overcome some limitation in scientific machine learning, Richard Feynman tells us in a lecture on computation that the physics is quite complicated, and we can discuss or solve problems with quantum mechanics. This is generally an idea on scientific machine learning and a novel paradigm in quantum scientific machine learning. Here we have something that is solved in a discrete setting by using a neural network. And here we have something that is related to approximation error. In the future, by using quantum scientific machine learning, this is a quantum neural network, you can have the solution of a problem as a linear combination of wave function, and in terms of approximation error, here there is no approximation error. In other words, if you have some limitation about approximation and total error in scientific machine learning, or some problem in optimizing eigen nonlinear function, if you will use the quantum framework, ideally the approximation error goes to 0, and it is quite easy to compute the minimum of high-dimensional nonlinear function by using a quantum circuit. Here there are some novel algorithmic and practical way to do this, and are tensor train networks and variational quantum circuit. For this kind of architecture, it is only a possibility. You can estimate the approximation error as inversionally proportional to qubit square root. About generalization error, you have some Richter-Meyer complexity, and you can tell some things about approximation error by using exponential convergence of stochastic gradient descent algorithm for optimizing the problem. Just for concluding my talk, I want to highlight you that by mathematical point of view, machine learning, neural network, and physics-informed neural network are well explained by mathematical point of view. For the general framework of scientific machine learning, we are only at the beginning. We try to explain some things. So the red light, the traffic light is yellow. But if you think at generative AI or quantum models, the mathematics is just at the beginning. There is no mathematics for this kind of topic. Now, in conclusions, a few years ago, deep neural network, this kind of methodology are viewed as, for mathematicians, as a magic black box, but now we have enough mathematics to explain some things in terms of efficiency and accuracy of a model. Physics-informed neural network are very known in scientific machine learning, but we have to more investigate the impact of physics-informed and AI by mathematical point of view, and surely we have to enroll young talents in mathematical foundation of quantum scientific machine learning. This is a brief overview of the bibliography of the talk, and I want to thank I want to thank your workshop, your center for inviting me, and I want to thank Vincenzo Schiano di Cola, that is a postdoc that works strictly with me on this topic, and guys of mathematical modeling and data analysis laboratory in Naples that collaborate to my research. This is all. Thank you.
Thank you so much, Professor, for this very interesting talk and very mathematical. So yes, now we have time for some questions. So if the audience have any question, they can ask for turn writing down their name in the chat. And in the meantime, I will also ask a question that is related with the what's the name? The complexity and in practical terms of these neural networks in comparison to normal fully connected or convolutional neural networks that maybe you have tried in some of your practical problems, like what is the difference in terms of time and memory consumption using these physics-informed neural networks?
Okay, sure. One thing I say that by theoretical point of view, it is more very important to measure the complexity of a network because it is strictly related to generalization error. But about physics-informed, in other words, if you have a deep neural network that is enough large, you can use the first layers of your network to acquire low pass information, and the other layers to have high details of your information. In other words, you can have an approximation of the problem in the first layers of your networks, and at the end the details for capturing dynamics. If you think in something as image reconstruction or image detection, you have to think to design a neural network that is enough large to capture some qualities of your problem. In the case of physics-informed neural network, you could have also deep neural network that are not so large in terms of memory, because you have physics and data that help you in recover the solution of your problem. So some things is in a certain sense adjusted by the physics and by the data in the learning feedback.
But in terms of time, what would be the
This
difference?
is about accuracy. In terms of time.
Yes, obtaining time, for example.
Oh, okay. In terms of times, it strictly depends by the dynamics of the problem. If the problem is quite complex, in the case of Navier-Stokes equation, for example, or turbulence and so on, you have to train for a lot of times and with a lot of training points your network, and the time is enough big. And also if you have to solve high-dimensional problem, the time is quite big. But if you want to use the physics-informed neural network in a pre-trained way, you cannot have enough a lot of time because the training is just done, and so you have only to recover the solution of your problem.
Okay, thank you.
Surely you need high performance computing. You need also for solving, for example, Black-Scholes. You have GPU, and you have about 1 hour of training times for the model.
So if there is someone that has more questions, they can write down in the chat their name. Okay, so I have one more. Okay. I have one more question that is related with the future research that you will have maybe in the if you thinking about importing other popular paradigms right now in deep learning that maybe could be interesting to apply in this physics informing if it's possible. For example, transfer learning or
Yeah. It's very interesting question because there are a lot of problems, for example, for complex physics, in which we can use deep reinforcement learning methodologies for solving the problem. You can model in some same reward functions and the state by using physical information. For example, for the reward, you can have some information about the form of your object. If you think at computational mechanics, for example, you have a fixed form to use for predicting, for example, temperature on this form, and you can use it as a priori information on the problem as a reward state in a deep reinforcement learning, and you can try to translate some things as state inside this complex physics. So you have to take the classical paradigms, for example, of deep reinforcement learning and translate it in a computational way. And I believe that a lot of just pre-trained models or just done feed-forward neural network as ResNet and so on can be for free enrolled inside the complex problem and use it as a tool. Because if you think at the Boltzmann transport equation, this equation is very difficult to solve by mathematical point of view, and it is very used in nano design of materials at nanoscale. So you could use deep learning methodology and transfer learning embedded inside this physical process in order to solve in an efficient way this very complex mathematical problem.
okay, so if someone else has questions, we have time for one more.
Okay.
Let's see.
I believe that the talk was quite mathematics mathematical subject, but I believe that it is important to have clear the foundation, because sometimes people take attention to the loss, but forget that everything is related to collocation points, to generalization error, and so on. And for computer scientists, they have to take into mind that if also the loss goes to 0, it is not ensured that the problem is well solved.
Yes, I believe that they will pay now more attention to that. So if no one has more questions, I think that we can let it
Okay.
here. Thank you so much for this talk, and yes, we will keep in touch. Thank you so much.
Okay, thank you for
Very
inviting
interesting
me,
talk.
and have a nice day.
Thank you, you too.
Bye-bye.
Bye.
Thank you. Bye.
Stop recording.